To discuss the technical maturity of ASNs, it makes sense to introduce the notion of technology readiness level, or TRL. TRL is a method for estimating the maturity of a technology, which allows for consistency when comparing technical maturity across different types of technology. The TRL scale ranges from 1, basic principles observed, to 9, the most mature technologies, with maturity determined through a technology readiness assessment that evaluates concepts, technology requirements, and demonstrated capabilities. It was originally developed by NASA in the 1970s and has been widely adopted by organizations such as the US Department of Defense, the European Space Agency, the European Commission, among many others. In 2013, it was formalized as an international standard by the ISO. While specific TRL charts, of which there are many, might differ slightly in wording, they by and large are consistent. We give and will talk through one such chart. TRL 1, Basic Principles Observed. At this level, scientific research begins to be translated into applied research and development. Basic principles of the technology are observed and reported, but practical applications are not yet considered. TRL 2, Technology Concept Formulated. The technology's basic principles are expanded into broader research ideas. In this stage, potential applications are identified, and the technology concept is formulated, but it remains speculative without proof or detailed analysis. TRL 3, Experimental Proof of Concept. Active research and development begins, including analytical and laboratory studies to validate that the concept works in theory. Initial proof of concept is demonstrated, but this may be limited to modeling or simple experiments. TRL 4, Technology Validated in Lab. The technology reaches the point where components or basic subsystems are tested in a laboratory environment. This stage involves a higher degree of integration of the technology's components, though it is still far from operational. TRL 5, Technology Validated in Relevant Environment. The technology is tested in a relevant environment that simulates the real-world conditions under which it will operate. This is a significant step beyond laboratory testing, with more realistic assessments of performance and limitations. TRL 6, Technology Demonstrated in Relevant Environment. At this stage, a prototype or model is developed and tested in an environment that closely resembles the actual operational conditions. This level demonstrates the system's ability to perform in an operational context, albeit on a limited scale. TRL 7, System Prototype Demonstration in Operational Environment. The prototype system is demonstrated in an operational environment, meaning it is tested under real-world conditions. The system is near completion, but it may still require some final refinements based on the demonstration's outcomes. TRL 8, System Complete and Qualified. The technology is fully developed, and its capabilities are confirmed through rigorous testing. The system is considered complete, and all subsystems have been integrated and qualified for deployment. And finally, TRL 9, Actual System Proven in Operational Environment. The technology has been successfully deployed and proven in an operational setting. At this level, the system is fully operational and meets all intended specifications and performance requirements. It is now considered a mature technology, ready for full-scale deployment. While the maturity of a technology could fall somewhere between two adjacent TRLs, which leads to a difficult decision for categorization, it is not hard to figure out the general area of TRL for a technology. Oftentimes, the first three technology readiness levels are grouped together as research, levels 4 through 6 are grouped together as development, and levels 7 through 9 are grouped together as deployment. These groupings are not always perfect, but they do give a good general idea of what these ranges of levels represent in terms of technical maturity. Something that is very important to note is that the TRL scale is not linear. It does not take the same level of cost, effort, and time to progress at each level. This has actually been the case with ASNs. ASN protocols and applications started to show a lot of promise several decades ago, such as two of the canonical ASC schemes, E91 and BBM92, being developed in 1991 and 1992 respectively, and quantum teleportation, which plays a key role in many ASC and distributed quantum computing protocols, being developed in 1993. ASN protocols and applications continue to be developed to this day and receive plenty of attention. Because of this, many recognize the promise of ASNs. However, there's a misconception that ASNs are currently residing at a low TRL, that is in the bottom half of this chart. Part of the reason for this misconception about ASNs is that it took decades for the hardware to catch up to the theory. Because progress was slow at the lower levels of the TRL chart, people assumed that trend would continue. However, as we just mentioned, the TRL chart is not linear, and progress has sped up greatly in the last few years. This is in part because the funding, interest, and education surrounding these networks has also greatly increased. We have seen many ASNs deployed and announced in just the last few years. For example, that's true of many of the ASNs shown on this map. We update this map often, however, with so many ASNs being announced and deployed, there's a good chance that it's not completely comprehensive. The networks shown range greatly in terms of size, scope, and purpose, going back to the point that ASNs are incredibly versatile. Some of the ASNs on this map are used, at least in part, for advanced secure communications, such as DARPA QuantNet, distributed quantum computing, such as QuantNet and AFRL, distributed quantum sensing, such as Chicago Quantum Exchange. Some are used, at least in part, as commercial testbeds, such as Brookhaven National Lab and EPB, and many are used for multiples of these use cases. We have been heavily involved in many of the networks shown on the map in the previous slide. It is important to note that not only are ASNs being deployed today, but from firsthand experience, we know that an ASN capable of multiple use cases and operational environments, such as employing certain ASC applications and being used as a testbed for research and development, evaluation, and verification of applications, architecture, hardware, interoperability, protocol, software, etc., can be stood up from start to finish in under a year. The applications deployable in an operational environment today are very impactful, but we are just as, if not more, excited about the applications soon to come. Each year, significant progress is made and more ASN applications are deployable. Beyond ASNs scaling quickly in terms of capabilities, the same is also true in terms of size and scope. As hardware continues to improve, many of the networks shown on our map will join together to create larger, more versatile, and more complex networks. ASNs will evolve into larger, such as national and even global scale networks, in a similar way to how classical networks evolved into wide area networks and the internet several decades ago. Because ASNs can vary so much in terms of use cases, size, etc., it is near impossible to assign one TRL to all ASNs. However, ASNs employed with many of the most promising use cases have or will soon be deployed in operational environments. Because of this, it is fair to say that ASNs do not have a low technology readiness level and are actually progressing quickly toward quite the opposite. In the near future, we will see ASNs having a huge impact in a multitude of important ways for many federal, industry, and academic organizations. This is no secret and is reflected by the huge recent boom in investment, interest, and deployment of ASNs.